9. Chapter 9 sort of puts together a couple topics in the last couple of chapters. It puts together the grams to moles sort of calculation and also the balancing equations. And what we're going to do is come up with calculations from the actual chemical equation, which is known as stoichiometry. And we're going to talk about basic stoichiometry problems, a little bit more complicated stoichiometry problems. But basically, these are the calculations that we do based on the equation to try to figure out how much product we would make, to try to figure out if we know how much product we made, how much reactants we started with. So these are really calculations that allow us to use the equation to figure out really all kinds of things about the reactions taking place. We could also use reactants to reactants and products to product sort of relationship. So we saw this, I think, in the previous chapter, but just a reminder, a couple of different ways that we could look at a balanced equation. And pretty much all of what we're talking about today, which is stoichiometry, always involves a balanced equation. So if you do not have that balanced equation, then you're pretty much wasting your time on the calculation because you will get the wrong answer. When we look at the coefficients, which is again how we balance equations, only changing our numbers in front, they do represent certain things for this particular reaction that we're looking at. We could say we have 2 molecules of H2 react with 1 molecule of O2, gives us 2 molecules of H2O. Really, for the most part, stoichiometry, our basic stoichiometry problems pretty much use what is sometimes referred to as the mole-to-mole relationship. And in this case, that would mean that there are 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2O. Again, where I'm getting these numbers from and really what stoichiometry is about is a conversion factor. So again, we're getting these numbers from the coefficients from the balanced equation. And a reminder that if there is nothing written there, again, that is 1, not 0. So that is assumed to be 1 in that particular case. The last relationship here is sort of that conservation of mass. Since in a chemical reaction, the only thing that changes is electrons and bonds. We don't touch anything in the nucleus. So we have conservation of elements. So in this example, if we have the 4 hydrogens on the left, we will end with the 4 hydrogens on the right. And since each hydrogen is about 1 gram or 2 grams here, we will end up with about 4 grams of hydrogen on each side. So let's talk about stoichiometry and really what we use these calculations for. It's really about a chemical reaction and our reactants and our products. And sometimes people get really sort of freaked out about the whole stoichiometry thing, but it really is just a conversion factor. So it's just a conversion factor. And the difference is instead of going to a table to sort of find that conversion factor, we use the balance from one thing to the next. And that's because in these type of problems, especially the basic type problems, you're oftentimes given information about somebody in the equation that you're really not interested in. So you need a way to go from whatever information they gave you to somebody else in the equation. So you can't find a table that tells you, how many H2s are in O2 and all that kind of stuff. So that's where the conversion comes from, is actually the balanced equation. So it allows us to figure out things, like I said earlier, if we put in a certain amount of reactants into a reaction, it can figure out how much products we should get out. We also could go the other way around. If we figure out how much products we produced, we could do some back calculations and figure out how much of the reactants we had to put in there to get that much product. So look at reactants to reactants. So we could do stoichiometry calculations between 2 reactants. So if we know how much of one reactant we're putting in there, we could calculate how much of the other that we would need to put in there as well. And we can also do that with products. So if we know how much, for example, of one product that we produced, we could use stoichiometry to figure out how much of the other product to produce. So the relationships, when we think about sort of the arrow, is we could do relationships on the reactant side in stoichiometry between 2 reactants. We could do the relationship between 2 products. We could go from reactants to products. We also obviously could go the other way around from products back to reactants. So we could apply stoichiometry really to anybody in the balanced equation. And that is really the most important thing, is that equation needs to be balanced. Otherwise, again, all the calculations is going to be off. So when we do these type of calculations, and we will see stoichiometry in many different areas, there are different units that we use. Grams and moles is very common for basic stoichiometry problems. And a reminder that if we are going from grams to moles, or even the other way around, that is the molar mass, grams per mole from the periodic table, that number on the bottom, that we use basically as a conversion factor to do so. So we definitely use that a lot in stoichiometry problems, at molar mass and that conversion of grams to moles back to grams. As we will see in other chapters, gas chapters, solutions chapters, we could have units that are in liters. We could also have some molarity in liters or volume as well. So the units will change, but really the basic steps to any stoichiometry problem is pretty much the same. It just varies just slightly different depending on what you're doing. The basis of it is what is referred to as the mole method, which is basically using those conversions, those coefficients from the balance equation as conversion factors to go and do these type of calculations. So there are some basic steps that you want to follow when you're doing stoichiometry type problems. There are 5 listed here, but really in most cases you could sort of cut it down to 4. The first step, though, sometimes happens is you want to make sure that you write the correct formulas of the reactants and products. So this would be a problem where you're given everything in words. So you would want to write the correct formulas like we were doing nomenclature. And then the most important of all of it here is really this next step, which is you want to make sure that you balance the equation. So again, it does not work right if it is not balanced. So if you see an equation is given to you, and you see no coefficients, you definitely should take a look at it really hard to make sure it's either balanced or not balanced, and you should balance it if it's not. If you see an equation, there's coefficients, it's probably going to be balanced unless somebody's trying to trick you, but you should also take a look at it just to make sure. You then want to pretty much, after you have the balanced equation, pretty much your next step is to convert things into moles, and you want to use the molar mass to do so. Now, these units could be any units, so you may have to do a couple of units or conversions to get there, but usually the last set of conversions is taking grams to moles using that molar mass from the periodic table. Once you have it in moles, that is where the stoichiometry part comes into play. You find that mole to mole relationship. And that's really the conversion factor that we get from the balanced equation that allows us to go from one thing in the equation to something else. Lastly, you usually want to convert moles to some other unit. And if you did everything correctly at that point, you should be in moles. But a lot of times they do want things like grams at the end. So the molar mass is oftentimes used at the end as well. So in a lot of cases, you may not run into this part of the step too often. So basically, you want to follow these 4 steps, balance the equation, convert whatever they give you to moles, find the mole to mole relationship, and then convert moles to some other unit. Pretty much all basic stoichiometry problems are these 4 steps. You should just follow these steps in the order, and it should get you to the right answer at the end. By the way, if something is done for you, don't undo it. So, if you're starting in moles, don't take them out of moles to grams and back to moles or anything weird like that. Just go to the next step. Any questions on that there? So let's take a look at an equation and how we can use stoichiometry. So as I mentioned before, really stoichiometry is just a conversion factor. And instead of going to like a table, as I mentioned, we go to the balance equation. And we could, from this one equation here, there are a few different relationships that we could get. And if we look at it, we're just looking once again at the coefficients in front. And we could say that for every 2 moles of CO we put in there, we also need to put in there 1 mole of O2. We also see that for every 2 moles of CO we put in there, we get 1 mole of CO2 out. And for every 1 mole of O2 we put in there, we get 2 moles of CO2 out. So once again, this is just the coefficients from the balanced equation. And these are what are referred to as being stoichiometrically equal to each other. These are basically equalities. Now, in the case of stoichiometry, equalities are not equal to each other. So clearly 2 does not equal 1, but it is a relationship of, I should put the right number there, so that would be good. 2 would be good. There we go. It is a relationship of what we need to put in there in terms of to get this reaction to basically take place. So again, if you were thinking about, when you make cookies or something like that, you got to put enough flour, enough chocolate chips and all that to get a dozen cookies out. This is the same idea. This is sort of the proportion of these things that we have to put in there to get out the product to basically occur. Now, these are equalities, and we treat them like equalities that we saw like in the beginning chapter. And any equality, you really could write some conversion factors from, and you can write 2 conversion factors for each equality. So in this case, we could say that there are 2 moles of CO over 1 mole of O2, or 1 mole of O2 over 2 moles of CO. So that is our first relationship. Our second relationship, we could say that there are 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. Lastly, here, we could say for every 1 mole of O2, we have 2 moles of CO2. Our 2 moles of CO2 gives us 1 mole of O2. So from this one equation, we were able to have basically 3 equalities and 6 different conversion factors that we could use in this type of problem. The idea here is you will not use all of them. You will just use probably the one that you need to solve the problem that you're looking for, but you do have all these available to you if you are doing different types of problems from this one equation. Any questions on the relationship or the conversion factors or where they came from? So for example, here, if we let's just say that we produced 17.5 grams of CO2. How many grams of O2 did we start with? So if we were going to do this problem, the first thing that we want to do, which is already done for us, is we would want the equation to be balanced. The second thing that we want to do is take whatever they gave us, which in this case is the 17.5 grams of CO2, and we want to convert them into moles, which clearly in this case we do have to do since they're sitting in units of grams. Remember, to go from grams to moles, we do need the molar mass. So we want to convert to moles. So to do that, we would need the molar mass of CO2, which comes from the periodic table. That's going to be 12.01 grams per mole for the carbon, plus 2 times 16 grams per mole. For the oxygen, going to give us 44.01 grams per mole as our molar mass for CO2. Remember, molar mass is also really just a conversion factor to do those conversions. So the second step here that we want to do is we want to take what they gave us. We're going to use the molar mass and set it up dimensional analysis so opposites cancel. So we do want the grams on the bottom, 4401 grams per mole of CO2. The grams of CO2 here will cancel. That's going to give us 17.5 divided by 4401. And if you got an answer, which you don't necessarily need to do, But if you did, you got 0.3976369. Again, here I'm going to take it out to a few more digits because I'm not done with my calculation and we don't really want to round too much at this point. Now we have basically done the second step, which is to convert to moles. The third step is the actual stoichiometry part, which is the mole to mole relationship. And when we go to the equation, we're basically looking for the two things we're interested in. And one thing that you're interested in is whatever they gave you. So in this case, they gave you the grams of CO2. So we're definitely interested in CO2. And we're also interested in what we're trying to find, which in this case is O2. So those are the two things we're interested in. We did this earlier. We used this equality that for 1 mole of O2 gives us 2 moles of CO2. This gives us basically two options for conversion factors here to use in this problem. And in this case, we do want to get rid of the CO2. We want to be left with the O2. Should I use the conversion factor on the left or the one on the right to do so? We should use the one on the left, as again, opposites cancel. So we do want the CO2 on the bottom. So continuing on with my non-rounded number here. The third step, which is the big stoichiometry step, which comes from the balance equation, we're going to go with 2 moles of CO2 on the bottom, 1 mole of O2 up on top. And once again, the moles of CO2 will cancel, and that's going to convert us into O2, which is what we're looking for. Basically just dividing by 2 in this case. 0.19882. We'll take it to a few digits. Moles of O2. Any questions on that so far? Now, in this case, if we happen to have wanted the answer in moles, we would be done. We'd have to round it up a little bit there, and we could have our answer. But we actually want grams in this case, so we do have to do the fourth step, which is to then convert those moles into some other unit. So the fourth step here is to convert our moles to, in this case, grams. It's important to remember, though, at this point, we are no longer with CO2. We have converted to O2. So we will have to go back to the periodic table and get the molar mass of O2, which in this case, obviously, is 2 times 16. Going to give us 32 grams per mole, which is our molar mass of our O2. So to finish out the calculation, I'll just get rid of some of these conversions we didn't use here, get a little bit of room. All right, so to finish out this calculation here, we would take our non-rounded number there, 0.19882 moles of O2. Using the molar mass there, 32 grams are going to go on top, so we end up with grams. Moles will go on the bottom. The moles will cancel. Timesing by 32. Going to hit us a 6.36 grams of O2 in this case. At this point, that's the end of the calculation. So we're going to round to sig figs based on this number here, which is pretty much the only number in the problem. Everything else pretty much could be considered an exact number, so you don't have to worry about it in terms of the calculation. Any questions on any of those 4 steps? Once again, here, I did get an answer after each step. You could just do it all in one calculation all the way through, which is technically how they want you to do it, really. But for me, I don't really care. If you want to do a step-by-step, you could get an answer. But you do need to show, obviously, all the work and try not to round to the very end. Any questions on that? So basically what that number represents is if you produce 17.5 grams of CO2, you had to put in there about 6.36 grams of O2 to actually get that amount out. All right. Let's take a look at some then. This is what we just talked about. All right, so why don't you try the first part up to here. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We're looking for how many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water. So give it a go, see what you come up with. Okay, let's take a look. So once again, in this case, we're not given actual equations, so we definitely want to start with that. And as we talked about when we're talking about equations, we want to make sure we start with the proper formulas. So lithium metal is just Li by itself, no charge as it's uncombined. Reacts with water, which hopefully you know is H2O. Forms hydrogen gas. A reminder that hydrogen, right, is a diatomic molecule, so should be H2. And lithium hydroxide is LiOH, as lithium is group 1 plus 1, hydroxide is minus 1. At that point, once I have all of my equations down, our formulas down correctly, then I can worry about the whole balancing thing. And I don't know, maybe like a 2, and a 2, maybe. I feel like I just put 2's everywhere, but I think that worked. So I think we got 4 on hydrogens on the left, 4 on the right. 2 lithiums and 2 oxygens on each side would give us our balance equation. Any questions on that there? Once again, this is always step that you want to do. Either you need to write the equation correctly or you need to make sure that it's balanced. Again, none of this is going to work. The next thing is here, they gave us basically 5.32 moles of lithium. In this case, we do not need to actually do number 2 as it's already done for us. So we shouldn't undo it just to do that step. So that means the next thing that we could do is actually go to the actual stoichiometry part. They gave us information about lithium, which is really not what we're trying to find in this problem. We're actually interested in hydrogen. So again, the stoichiometry from the equation is going to allow us to use it as a conversion factor. And from the equation, there are 2 moles of lithium, gives us 1 mole of H2. Once again, from that, we could actually get our 2 conversion factors, which is available to us, which is our 2 moles of lithium over our 1 mole of H2, or our 1 mole of H2 over our 2 moles of lithium. So in this case, we are looking to get rid of lithium. So opposites cancel. So we will want to use the conversion factor here on the bottom to do that. And that will put us 2 moles of lithium, gives us 1 mole of H2 in this case. The moles of lithium cancel. And essentially here, divided by 2, gets us 2.66 moles of H2. In this particular problem, that is actually what we're looking for. So we're actually looking for the answer in moles. So that means that we actually do not need to do number 4, but it is those steps. So step 1, step 2 was done for us. Step 3 was just stoichiometry. And in this case, step 4 was not needed. Any questions on any of those steps there? All right, then why don't you try the next part of the question here, which is here. So using the same equation, we're looking for how many grams of H2? Let's do both, actually. Let's do grams of H2 and grams of lithium hydroxide in this case. So let me give you some information that might be helpful. Lithium 6.941. Hydrogen 1.008 and oxygen 16. All right, so take a few minutes, same equation, same reaction, starting with 81.75 grams of lithium. How many grams of each product would we produce? And basically follow those steps. Yeah. Okay, so let's see how you're doing. So once again, we want to start with our 4 steps here. Obviously, we already did our balanced equation, so that's good. In this case, we are given lithium there in grams, which means we do need to convert it to moles. So that's really the second step that we want to do, is take what they gave us, which is 81.75 grams of lithium. Using the molar mass of lithium from the periodic table, we want the grams on the bottom so that they cancel, and moles up on top. And that's like our second step. The grams of lithium would cancel right at this moment. Once again here, if I wanted to, I could get an answer, or I could just continue on with the calculation. So in this one, I'm going to just continue on with the calculation. So at this point, we have moles of lithium, and we need it in moles so that we could do the actual stoichiometry. So in this case, it's the same relationship that we saw in the previous problem. We were looking between lithium and want to end up over here to hydrogen. And that's really what stoichiometry allows you to do, is to kind of convert over to the hydrogen. And from the equation, we can see there are 2 moles of lithium for every 1 mole of H2. That again gives us our 2 conversion factors that we could use. The 2 moles of lithium over 1 mole of H2, or the 1 mole of H2 over the 2 moles of lithium. So if I were just to continue on here with our calculation, also why we want to set it up dimensional analysis, we could see clearly that the moles of lithium are up on top. So to allow those to cancel out, we have to put lithium on the bottom, which is the opposite location. So the moles of lithium, 1 mole of hydrogen from the balanced equation, which is the big stoichiometry step right there. That's going to get rid of our moles of lithium. And if we stop right at this point, we are in moles of hydrogen, which again, if we wanted the answer in moles, we would get the answer, clean up some significant figures, and we would have our answer. In this case, though, we do not want moles as our final answer. We do want grams. So we do need to do the 4th step, which is to take those moles, which you should be in at this point, and convert them into grams. It's important to remember once again that we are no longer with lithium. We have now transferred over to H2. So we do have to go to the periodic table and get the molar mass of H2, which in this case is our 2 times 1.008. By the way, once a reminder again that when you take the molar mass from the periodic table, or in general, when you calculate the molar mass, usually 4 significant figures is how much you go to. We're going to use this as a conversion factor. And again, we see our moles are on top, so we want the moles of H2 on the bottom, 2.016 grams up on top. We're going to multiply whatever's on top and come back through and divide by whatever is on the bottom in this case. And that gets us 81.75 times 2.016 divided by 6.941 and divided by 2. Looks like 11.87 grams of H2 at this point. Significant figures based off of the original number there, which has 4. Any questions on any of that? Yeah. What if the last number after the decimals? I would think you should be fairly close unless you did some rounding. If you did a little bit of rounding, it's probably okay. If you did get an answer after each step, once again, don't round too much until the very end. And again, if you take about 4 significant figures off that periodic table for the molar mass, you should be pretty close to most people's answers. Yeah. Other questions? So what this basically means is if I put into this reaction 81.75 grams of lithium, great. 11.87 grams of hydrogen. This is what is referred to as the theoretical yield. A yield is always a product, and it is basically your maximum amount of product that you should get out in this reaction if everything went perfectly. And again, nothing bad happened, no side reactions. Any questions on that one? Now I added on to this one. We also want to know the grams of lithium hydroxide. So there's really two things that you could do at this point. You could, you know, hike back over here and kind of continue down this path. And instead of using our lithium to hydrogen relationship, you then could use our lithium to lithium hydroxide relationship, which in this case is 2 moles of lithium equals 2 moles of lithium hydroxide. And you basically would have our 2 moles of lithium and our 2 moles of lithium hydroxide. You then could use the molar mass of lithium hydroxide, as the moles of lithium would cancel. And lithium hydroxide in this case is 6.941 grams per mole, plus our 1.008 grams per mole for our hydrogen and 16 for our oxygen. Gonna get us about 2375 as our molar mass. And just like we did before, we would want the grams up on top. Per mole lithium hydroxide, those would cancel, and obviously we would still have this conversion as well. Moles of lithium, 6.941 grams of lithium. And if we did that, 81.75 times 2 times 2375 divided by 6.941 and divided by 2. And I guess it would help to get the right number there. 95 was close. 95. All right, so try it again. 95 times 2 times 81.75 divided by 6.941 and divided by 2. Gets us 282.1 grams of lithium hydroxide. That would be the theoretical yield of our other product. First off, basically it's the same calculation. Obviously here, 81.75 grams of lithium. Now, you don't necessarily in this case need to go all the way back to the beginning. You could have started with your hydrogen as well. So in this case, we could have done, I know I produce 11.87 grams of hydrogen. I could do the mole to mole relationship between hydrogen and lithium hydroxide from the equation. But before I could do that, I got to convert it into moles. So 2.01 grams of H2 per mole of H2, which is the molar mass we used earlier. And that's going to get us into moles of H2. And at that point, we have 1 mole of H2 gives us 2 moles of lithium hydroxide. The moles of H2 cancel. And a mole of lithium hydroxide is our 23.95 grams of lithium hydroxide. Those guys cancel, gets us back over there. So you could do it from the product and just go back to the next product next to it. You don't necessarily have to go all the way back to the beginning, or you could go from the beginning. They both will get you the same answer. It's still the same 4 steps, really. Convert to moles, mole to mole relationship, and moles to some other unit. So with stoichiometry, you have the relationship of everybody. You can stay on the same side of the arrow, go back and forth. They all should get you the same way if you do the same 4 steps. Any questions on any of that there? Now, obviously, if you got an answer along the way here, you would have the moles of H2, and you could have just picked it up from that point as well if you did get an answer after each of those steps and just jumped over to the lithium hydroxide. Any questions on any of those steps there? Okay. All right, so why don't we try another? All right, so why don't you try this one? If you have 765 grams of C6H12O6, how many grams of CO2 would you produce? Carbon 12.01, hydrogen 1.008, oxygen 16. Again, follow those 4 steps there. Okay, so let's take a look and see. So again, basic stoichiometry problem. We're going to have the balanced equation, which was given to us. I see some coefficients, and it does look like it is balanced. We are given basically 765 grams of this guy. We ultimately want to know how many grams of our CO2. So this definitely is a stoichiometry problem. We do have to convert our grams into moles, which is our second step that we want to do. So we will need the molar mass from the periodic table of our C6H12O6. So basically here, we're just going to add up all the parts. So that's going to give us 6 times 12.01 for our carbons, plus 12 times 1.008 for our hydrogens, and plus 6 times 16 there for our oxygens in this case. Adding all that together gives us about 180.2 grams per mole, which would be our molar mass and really our conversion factor to convert from grams to moles. So that is where we will start. 765 grams of C6H12O6. Once again, going opposites to cancel, so grams on top. So we do need the grams on the bottom here to cancel out. Once again, you could get an answer or you could continue on with the calculation. I'm going to continue on with the calculation at this point. If you do get an answer, try not to round too much. But basically, we are at moles of our C6H12O6, which is good because then we are interested now in the stoichiometry. That's going to allow us to go from this guy, which is what we were given, over to this guy, which is basically what we're looking for. And it is nothing more, again, than the coefficients from the balanced equation. And from the balanced equation, we see that for every 1 mole of our C6H12O6, we get 6 moles of our CO2, which is what we're going to use to do our conversion. So to cancel out the C6H12, we're going to put that on the bottom. And our 6 moles of CO2. Once again, you could get an answer or continue on with the calculation. Regardless of what you do, you should be at units of moles of CO2 at this point. That's close to what we're looking for, but we are looking for grams. And that means we do have to do step number 4 here, as we did that. So step number 4 is to convert our moles into grams. Once again, we have converted over to CO2. So we do have to go back to the periodic table to calculate the molar mass of our CO2, which we might have used earlier here. And that's our 4401 grams per mole. So the last part of the calculation here, moles on the bottom, so they cancel, grams up on top. So we are left with that at the end. The moles cancel. Once again, multiplying across the top and dividing by the bottom there. 765 times 6 times 4401 divided by 180.2 looks like. Gets us about 1,121 grams of CO2. Sig fig wise, looks like 3 is maybe where we should end up. So maybe something like 1120 grams of CO2 would be good, yeah. Any questions on that there? This once again is the amount of product that we should produce. So again, that means if we threw 765 grams into this reaction, we should expect about 1,120 grams of CO2 out. That once again is our theoretical yield. Yeah. Any questions on any of those steps? Again, same 4 steps: convert to moles, mole to mole relationship, and moles to some other unit. Yeah. Any questions? Let's try one last one here with basic stuff. How many grams of our cisplatin, whose molar mass is 300.1 grams per mole, can be obtained if you started with 0.7752 grams of K2PtCl4? This is okay. So once again, here we are starting with 0.7752 grams of this guy. We eventually want to get to grams of that. That is, again, a stoichiometry situation. We have our equation, which is balanced. So the second thing that we want to do is take whatever they gave us basically and convert them to moles. And we do need to do that. They were nice enough to give us the molar mass. If they didn't, obviously you would need to go to the periodic table and add up all the parts to get there. So 0.7752 grams of our K2PtCl4 using the molar mass that was provided, 415.1 grams per mole of our K2PtCl4. The grams are going to cancel out in this case. And that is, again, the second step that we want to do. That basically puts us into moles of our starting reactant here. Now we can use the stoichiometry from the equation and looking at our guy here and here, not too bad. It looks like it is a 1-to-1 relationship between those. So as we can see there, for every 1 mole of our K2PtCl4, we get 1 mole of our product there, PtNH3 to Cl2. So that makes the stoichiometry pretty simple. 1 mole of the K2PtCl4 go on the bottom so that they cancel. The 1 mole of what we're looking for will go up on top. And again, if I stopped right at this point, we would be in moles of our product. But again, here we do want grams, so we have to do that 4th step of taking it from moles to grams. Once again, they were nice enough to give us the molar mass in this particular problem. Otherwise, you would have to return to the periodic table there to calculate it yourself. And we're going to use that there to do the 4th and final step of our calculation, which is a mole of our product here. Has a molar mass basically of 300.1 grams. And if we do all that, multiplying across the top there, 7752 times 300.1 divided by 415.1 gets us 0.5604 grams of PtNH3 to Cl2. This, once again, is a product and how much we should get out of this reaction. Also, once again, our theoretical yield in this case. Any questions on any of those steps? Hopefully you can see a pattern. It is just those same 4 steps repeated in a basic stoichiometry problem, which is pretty much what these are. What makes them a basic stoichiometry problem is you're pretty much just given one piece of information about a reactant, a product, just one piece of information that you could convert to moles. That's how you know it is a basic sort of problem. Any questions on any of these basic problems here? All right, then let's talk a little bit about non-basic problems there. So limiting reagents, or sometimes referred to as limiting reactants, are situations where when you have a reaction that takes place, there's usually one reactant that gets completely used up, and there's one that you, that's what creates limiting reagents. So is the reactant that gets used up. And then there's one that's referred to as the excess reagent, which you have plenty of. So when we have a limiting reagent type situation, For example, if we have A plus B makes A and B, obviously in order to make our products here, we do need A and B to come together. And let's just say, for example, here that A was the limiting reagent and B was the excess reagent. The importance of that is what would happen as soon as I run out of A? Could I make any more products? I could not make any more products because I don't have the A there to make the products. So when it's a limiting reagent situation, it's really important because it is always the one that determines how much product that you can make. So as soon as it gets used up, you cannot make any more product. So the limiting reagent is always the most important. In how much product you could produce. So the good news is in terms of limiting reagent type problems, they're very similar sort of steps that we do in a basic stoichiometry problem, except somewhere along the way you need to figure out which one's the limiting reagent, and that will tell you how much product that you will make. So as I mentioned, we always will have some reactant that gets used up first, which is why sometimes people call them limiting reactants. Same thing, limiting reactants, limiting reagents. And once that gets used up, there's really no way that you can make any more products. So when we do our calculations based on the equation to try to figure out how much product we should produce, it should always be based off of that limiting reagent, as it will determine, again, how much of that you can produce. The excess reagent obviously is the one that we have plenty of still there when the reaction is over. So for example, here, if we're going to make some workout buddies and we got 5 on the left and 3 on the right, our limiting reagent looks like the guys over here, right, is our limiting reagent. We're not going to be able to put them together anymore after we run out of 3 of them, which is going to join up with 3 on this side. We also can, in this type of problems, figure out how much of our excess reagent is left over. So for example, here we would have 2 of our excess reagent left over as a result of this reaction. So those are very common sort of questions that you're asked in these problems, which is, how much product would you produce and how much of your excess reagent is left over. So let's take a look at an equation such as this, and let's talk about how we can determine which one is the limiting reagent and which one is the excess reagent. There are a ton of different ways that you could do these problems. So I'm going to show you one way, and I'll talk about another way that's very commonly used as well. But there are actually 3 or 4 different ways you could kind of do these type of problems. So when we have this, let's just say, for example, we are starting with 4 moles of sulfur in the above reaction, and we're going to mix it with 20 moles of fluorine. And this is really our starting amount of each of those reactants. So here's the deal. First off, this is how we know that this is actually a limiting reagent problem. And we know it because we are given enough information to figure out the moles of each reactant. So that is a clue to you that if you are given whatever the units may be, but enough information for your 2 reactants to figure out moles, then it is a limiting reagent problem. So if you think about all the basic stoichiometry problems we did previously, you pretty much only had one piece of information. So that is the big key of, oh, they told me I'm starting with this much of this and this much of that. So that is a limiting reagent problem. The good news is the first several steps are the same. So you're going to start with the balanced equation, which it is. You're going to convert to moles, which was already done for us. So once again, if they were in grams, we would convert them to moles. So one approach that we're going to talk about as to how to solve these problems is you will basically do just a small little stoichiometry type calculation. And what you're trying to figure out is, if I want to use up all of one of my reactants, how much of the other one do I need to toss in there to do that? So that's basically what this calculation is. So for example, if I want to use up all of my sulfur, how much fluorine do I need? So I'm just going to do a basic stoichiometry calculation between sulfur and fluorine. So if I started with my 4 moles of sulfur, from the equation, I can see that for every 1 mole of sulfur, I get 3 moles of F2. So we're going to use that as a relationship. And we will have 1 mole of sulfur and 3 moles of F2 on top. The moles of sulfur cancel, and that's going to give me 12 moles of F2 is needed. So what this little calculation is telling us if I wanted to, like I said, completely use up all the sulfur, I would need to put in there 12 moles of fluorine. So how do I know if I have enough? I'm going to look at how much I need to how much I'm starting with. So in this case, do I have enough? I need 12. I started with 20. I do have enough in this case, right? So when I compare that, I do have enough. And because I do have enough, that tells me that the F2 is the excess reagent. And by default, that means that the sulfur here would be our limiting reagent. So that little calculation right there basically allows us to figure out which one is the limiting reagent and which one is the excess reagent. Question on that calculation? Now, I happen to have chose fluorine and sulfur, like how much fluorine I need to use up sulfur. You could do the other reagent. It doesn't matter which one you choose. They will tell you the same thing. So if I chose the other reagent, and I want to know how much to use up all of my fluorine, how much sulfur would be needed. I would do a similar calculation, except I would start with my moles of fluorine. I would use my same relationship from the equation, and I see that it is 3 moles of fluorine gives me 1 mole of sulfur. The moles of fluorine cancel, so we're going to take 20 divided by 3. Gets me 6.67 moles of sulfur is needed. So now when I go to compare how many moles of sulfur to the moles of sulfur I'm starting with, do I have enough in this case? I do not. So it tells me the same thing. It tells me again, sulfur is my limiting reagent, and by default, fluorine would be my excess. Any questions on those calculations? You do not need to do both. You could choose either one. They both will tell you basically the same thing. So this is important because now that I know that my sulfur is the limiting reagent, that is the one that's going to determine how much product we will produce. So we will go back to the starting amount here. And in this case, we have 4 moles of sulfur. And now we want to figure out how much product we would produce. So between sulfur and our SF6, it's a 1-to-1 relationship. So 1 mole of sulfur gives me 1 mole of my product. And that should give me 4 moles of SF6. And that would be my theoretical yield in moles in this case, which obviously if I wanted grams, I could take it one more step further and calculate how many grams of SF6 that would be. Question on that. So this is one approach to figure out limiting reagents, which is you do a small little calculation between reactants and figure out how much of one reactant you need to use up the other and figure out do you have enough or not. The other common way is you just do simply 2 calculations from beginning to end, and whichever one produces the smallest amount of product is your limiting reagent and your theoretical yield. So if you just want to do 2 calculations, you could do that. You could do this type of step. There's a couple other ways you could do them as well. So there's multiple ways you could do it. We will talk more about this in the next